Welcome back, everybody. Welcome back to the channel. So today we're going to be continuing talking about parsing expressions, or more specifically, parsing primary expressions. And in today's episode, we're going to be talking about how to basically parse a .class expression and parsing a self expression. Now, this one's a pretty big one, so this video might be a little bit longer, so just be prepared for that. And before we get into talking about how to parse this information, I want to mention something very important. So, as you guys know, we're kind of going through and parsing, or I'm showing you guys how to parse an expression. And of course, you guys know that I also update my roadmap file pretty frequently. Now, I was thinking that maybe I wanted to add another important feature, but what that would require me to do is basically show you guys how to parse this on the parser side. And what the feature is it's basically called code obfuscation. So if any of you guys have ever coded in Android before, you guys know there's a thing called ProGuard, which basically allows you to obfuscate your code so that way other developers can't reverse engineer your source code if they pulled your application down from the Play Store. Now, me being kind of Android centric, I've been doing it for several years now. I really like this feature because I think that it definitely secures your code a lot more, but I'm not sure if whether or not I should add this in. This is going to be quite a big feature. It's not so complicated on the back end side. It's more complicated on the front end where I have to parse all this stuff. So if I get at least one like on this video, then I will add in this code. It's not going to be that much work, like I said. So if anyone's interested in trying to basically figure out how you add code obfuscation to a programming language, I think this is a cool feature. Like I said, like the video, and if I get at least one like, then I will add this in. So moving on, let's go back to our parser here, and let's start looking at how we are going to parse this data. So I'm going to go here to syntax, our handy dandy file that we've been using, and now we are going to look at .class. Now, what this is this is basically like .class in Java. There isn't really a feature for this yet. I am looking to add something into my language where, like, if you have like an if statement, you can say, let's say foo field is here. Let me go to my standard library. So I have a couple files in here. I have let's just pick one. So let's pick a string, right? So let's say it's equal to a new string of some data, and yeah. So the feature that I wanted to add was I wanted to say if foo field is, and then we can say string dot class. And what that'll do is that will basically compare whether or not this foo field is the class of string. Currently, this feature isn't in the language yet, so this is something that we can use for later on, and I'll explain how we can add this feature in later. We don't have to worry about this not being in the language right now, but I just wanted to kind of explain why we need this .class feature. All right, so now let's go and look to see how we actually process this. So first thing you're going to want to do is you're going to want to enter protected mode, just in case this isn't what we think it is. You want to, of course, store the current token so you can restore it later. And you want to parse a utype. Now, we've gone over this several times, so I don't think I have to go over what that means. After you parse a utype, then you want to check to make sure that the next token is equal to a dot, and the one after that is equal to a class. So if you have your, in this example, string dot class, and here I'm actually going to take this code and replace it here since we're using variable declarations as a way to print out what we're processing. So after you do that, you add the tokens and then you fail the error management system, meaning that this doesn't mean that errors will be reported. It just means that if there were any errors generated as a result of whatever we processed, then we want to print them to the console. After that, you want to encapsulate. So that means that you want to basically take this branch that was created under this AST here, primary expression, and encapsulate it inside of this AST. And then finally, we have our after processing if statements, I guess you could say. Same thing like we had up here. You want to be able to process other things just in case maybe there's something else that the user wants to process. Now, as you can see here, I have a increment and decrement. I'm probably just going to block that because now, after thinking about it for a few minutes, it doesn't make sense. Basically, what that is allowing me to do, or allowing the user to do, is if they say, string.class to increment this value or increment the address. The concept of how this is going to work on the back end is, if we look at our example again, where we say if foo field is string.class. If we look at that, the way that this is going to work is this is going to effectively be a is instruction, or it's going to be a single instruction that's going to be generated in our virtual machine from our compiler. And we're going to effectively take the address of this object here and compare the class address of this object to the class address that is returned from here. So all string.class is expected to return on the compiler's backend is an integer. So you could literally say string class address, and you can assign string dot class. And what that'll do is that'll just give you the address of the string class. So it's basically just a number, but at the language level, we're adding language level support to be able to compare that syntactically. So, but it doesn't make sense to allow the user to plus plus that because that's just bad programming. So I'm going to physically block that. All right, so I've updated the code. So now basically, if there is a increment or decrement, we are going to say unexpected symbol. Now you need to be dynamic because it's one or the other. So you need to pass in the peak at next token into the error, so that way we can print out which one is broken. And then of course we don't support anything else happening after string.class because there's nothing you need to do after string.class directly. So we don't allow dots, so we don't allow like string.class dot some value, because it doesn't make any sense. We don't allow left brace because this is not an array, and we don't allow, or we do allow as. So I guess you can convert this to an integer, so like you can say as int. Now, this isn't really, this is going to be one of those things that's not recommended in the language specification. Obviously, this is going to return a number, but you shouldn't be doing this. It's kind of weird, but I guess we can support it, whatever, it's fine. So if the user wants to cast it, it's technically legal to do that because it does return a number. So we will allow the user and say if the next token is equal to as, then go to the as expression. Otherwise, we return true because we processed it successfully. Now, if we did not process this successfully, meaning that the next token after we parsed our utype was not a dot and a subsequent character after that was not class, then we want to free the last sub because we created one sub AST here. Otherwise, if we didn't parse the utype correctly at all, then we want to free up the last sub again because we created one sub AST here. And then of course, after that, so if you get to this point, that means that you didn't process it correctly. So of course we want to pass our errors, meaning that we're just going to ignore whatever the hell we complained about, and we want to reset the current token to whatever the old value was. So let's just kind of go really quick and see how this is going to look on the compiler side. So I'm going to go to parse variable declaration and uncomment the code, and we can see how it looks. All right, so here's how the formatting is going to be for a utype class expression. So we have our string.class here, and if we look in our primary expression, we have our correct AST, so that's looking good. We have our tokens of .class. You don't really need these tokens, so you can omit those if you want. I just have them because I didn't specify whether or not I wanted to get rid of them. And after that, you have your utype. So this is really all that's important here. So you have the utype of a type identifier reference pointer of string. So on the back end of our compiler, you can't do something like object because object is a keyword. Now I had syntax highlighting for these files, but I had issues with my IDE, so I had to completely destroy the old IDE and upgrade it. But in the process, I forgot to bring over my syntax highlighting, so I lost a bunch of crap, which is unfortunate, but I'll eventually get back around to adding syntax highlighting to the language, so that way we can kind of differentiate some of these characters here. But based on my language, object is a actual native type. just like var is another native type representing a number or subsequently underscore int64. So this is a int64 native type supported by my language. So on the back end, we're going to have to basically make sure that what we're processing as .class is in fact a class. And if so, great, we will process it and return the address of that class. Otherwise, if it's like a native type, then we complain about it. But we don't have to worry about that now. We can focus on that later. So that is how we process .class. Hopefully that wasn't too difficult. So now let's kind of see how we process dot notation call expressions, which this is going to be pretty big. So we're going to now process a self expression. So here, let me put some code here, self dot, and then let's say I have size of int, and let's say self.size is equal to, or probably not that. Let's just say self.size. I'll just do that. To keep things simple, so this self expression, as I've mentioned before, is basically like this in Java, but it's self in our language. And at the high level, processing self is not that complicated, but when you start getting into parsing dot notation call expressions, it gets a bit difficult. But this is going to be pretty fun because after we process this, today we will be able to compile function calls. So that's nice. In this case, this is a bit different. So this type of expression is what I call an absolute expression. I totally made up that word, so if you look that up, you're probably not going to find anything about it. But basically what that means is these type of expressions here, like when we're processing this information, we have to figure out, is what we're processing a literal? If we're processing like a dot class expression, we have to see, is it a dot class? But in this case, we're checking to see if the next token is self. So if it is, we know absolutely it is a self expression, no question about it. If there are any errors, then we need to report that to the user directly. We don't need to set up our error management system to put it into a protected mode because we physically know that what we're processing is in fact guaranteed to be the expression that we're processing. So that's kind of why you don't see protected mode around here. So like I said, once you expect your self token, then the next thing you want to do is the formatting. So the formatting is going to be self pointer and then dot notation call expression. So we check to see if the next token is equal to a pointer. Now, before we get into this, because this is going to be a rabbit hole, let's just kind of look on the outside first. So if we don't have a pointer, because it's not required, you can just have self, right? Because what if in a function, so we have our player class, right? Let's say we define a function called set shoes, and let's say we pass a shoes object, shoes, and in there we, do some code. Now I don't have to really write anything, but you guys get the point. But then we want to return the player class. And the point of this is, let's say we have like another function called setup player. And in this function, we basically have like a basic setup. So we have shoes of type shoes. Let's say we also have a shirt here um, of shirts and so on and so forth. I don't think I have to write the rest, but you guys kind of get it. So let's say we create a player object, player is equal to new player, and we say player dot set shoes, and we say shoe. And now what happens if you want to do like method chaining, right? So you want to say dot set shirt. So this basically allows you to do method chaining because you're returning the instance of the player class. Now let's also imagine that these functions are not inside the player class. Let's say they're in some outside function in some other like file in some other library, and we're creating this player class here that we created, and we are method chaining. So in order to properly do that, we need to support just processing self in our programming language. So after we're basically done setting our shoes, we can return self. And what that will allow us to do is return just the instance of whatever class that we are processing. So again, just like return this in Java, but it's self in our language. So if we go back, so whether or not we parse the pointer is neither here nor there. We encapsulate all of our information into a self expression. So we do that, and then we check to see if the next value is not equal to an as. And if so, then we want to set the branch equal to the self expression. So again, I'm calling get sub AST for whatever reason. That's really retarded. Get last sub AST. Okay, so you want to basically assign the branch equal to the last sub AST, which is this one. And you want to do that because if you guys remember, when we call increment and decrement, when we call dot or left brace, what these are going to do are these are going to encapsulate the expression of what it's processing inside of whatever the next expression is, right? So for instance, if we're processing increment and decrement, we want to set the branch equal to get last sub AST, so that way when we create and encapsulate a increment expression, then we will have this self E inside of that increment expression. So hopefully that makes sense. Now the reason why we're not doing it for as is a bit of a different situation. So when we process, like, let's say self as some other class here. So if we want to represent this class as some other class, what you're going to want to do is you're going to not want to encapsulate the value in the as expression. What you're going to want to do is you're going to want to have one expression to the left and one expression to the right. So this is going to need to have two expressions. And if you guys remember, the concept of encapsulation is to just cram everything into one AST. So we don't want to do it that way. It's just merely making sure that we format our ASTs properly. So we will see that and how it looks when we get down to processing as. But for right now, just know that that's kind of why I am doing this. So as you can see here, before we get into parsing a dot notation call expression, what we need to do is we need to check to see if the next token is an increment or decrement. Go to check increment. If it's equal to a dot, go to dot not, which means parse a dot notation call expression. And you don't have to worry about not having these labels here. You can just, like I said, comment it out or create the labels lower in the function. And when we get to it, then you can fill in the information necessary. So after that, you have your left brace. So let's say, I don't know, what happens if, we say self.size and size happens to be an array. Well, I mean, this is a bad example, but let's get the point. Then that allows us to parse an array expression. So we want to go there. Otherwise, as mentioned before, if we see as the next expression, then we go to as expression. Then after that, we return true. So we're always going to return true for self expression, even though we may have had errors through processing this. Like, I don't know, I may have done some really retarded, stuff here. That's besides the point, right? We know that this is an absolute expression, so we know that we've at least successfully consumed the information that we needed to. So for absolute expressions, we always want to return true, and you can see that throughout my expression parser. So for base, I return true regardless of what happened inside of here. Same thing for new expression, I'm returning true as an absolute right at the bottom, so on and so forth. So just keep that in mind when we're processing absolute expressions. So now, what the hell is a dot notation call expression? So first you're going to want to create this function. Now, dot notation call expression is a name that I created a while ago, which basically means that this function is going to represent everything for dot notation processing. So you have stuff like size. Technically, this is perceived as a dot notation call expression. Now, even though there aren't any dots in it, like I'm not saying size dot get value, for instance, even though there's none of that, this is still considered that because dot notation call expression uses U types to figure out how to format everything. So you either have generic U types where you can say a variable name dot some other variable. So you can have, size dot some other var, or specifically let's have an example here. I'm going to go to primitives. So I'm going to go to my primitives file. And in my primitives file, I have this value field. Well, I mean, this value field technically should be private. I'm still working out the standard library, but let's just assume that value currently is not private. We can say size.value, and now this is technically considered dot notation call expression as well because we use dot notation format to access the value field. You can also say too long, or too long. So like, let's say we have, this size, but we want to convert this size into a long. You say to underscore long, and now our size is a long class. Now this is where the call expression comes in, right? So you've seen the dot notation part of it where I have size dot value. This is the call part of it where we're also allowing support for processing function calls. So I don't want to keep rambling. So let's kind of see how everything looks. So first thing you want to do is create a dot notation call expression, and then you want to check to see if the next token is equal to a dot. If so, you want to add that token and push on. Now the reason why you want to do that is because we recursively call into a dot notation call expression. So that's kind of why I have this right at the top here. So that way when we're recursively calling into it, we can just continuously process information. So, dot notation call expressions, as mentioned, are centered around parsing a U-type. So this is parsing a U-type naked. Now, before we get into what a naked U-type is, let's kind of look to see what happens if it's not a naked U-type. So if it's not a naked U-type, I know that name is just so retarded. Um, If it's not a naked U-type, then we decrement the current token because maybe, I don't know, it's not what we expected. So we decrement the current token and then we return false. Otherwise, we return true. We don't really return anything inside of the if block of parse U-type naked. So we're just going to return true once we get down to here if we don't run into any errors. So that's pretty much the outside look. So now let's see what a U-type naked is. So here, a U-type naked is basically just a U-type. The only difference is it doesn't have these brackets. That's the only difference. Literally, there's nothing different here. As you can see, these functions are exactly the same. The only code that's not applied is that. So that's what that is. So after that, we want to basically peek forward and see if we have a left paren. Now this is where we get into processing a call. So now in this example, I'm going to walk through how this is processed before we even start looking at what the compiler is going to generate. So first thing we do, we come into our expression parser and we get down, it's not a literal and it's not a utype.class. So now we're processing a self expression. So we process self. So we consume the self character, we consume the pointer character, as you guys remember, and then we parse a utype naked. Well, that's going to consist of this information here. Now that we've processed a utype naked successfully, we want to check to see if the next token is equal to a left paren. If so, which in this case it is, then we parse what's called an expression list. So I have a begin char and an end char here, and this function is used in multiple places. So basically, you need to provide the start and end character that encapsulates the expression list. So in here, it's pretty self-explanatory. It's just a loop processing expressions. So all you do is create a expression list branch, and then you expect whatever your begin character is. You check to see if the next token is not equal to the ending character. So in this case, I don't have any expressions inside of here, so it's completely safe to just call a function with no arguments. So that's why we do this check. But if we do have arguments, then we parse an expression, and then we check to see if the next token is equal to a comma. If so, expect the comma, parse the next expression, go back up to the top, rinse and repeat. And then after that, of course, we want to end the function with processing our end character. So if we go back, we can see that parsing expression list is how we parse function calls. And of course, if we end up finding a left paren, then this is now considered to be a dot notation function expression. Yet another great name. So we basically encapsulate this value. So we encapsulate the naked U-type. We also encapsulate the expression list that was created as a result of the naked U-type. So we have both expressions inside of this AST.function expression. After that, we want to basically add support for, so like you guys can see it here, right? So like, what if you have a function with plus plus, minus minus? What if you have a function, here, let me add this as well, function, and you call it, and it's an array? Well, you can say or, you can have a function with a left brace, and you can have like some index value and closing brace, because obviously functions can return arrays. Or even better, you can have a function or function that has dot sum field. So like, or you could have this other case where you parse another dot notation call expression, which basically allows you to have a function, dot, and then some other field, because obviously functions can also return classes. So if you look here, this is pretty straightforward. You have basically just a check to see if the next token is in fact a increment or a decrement. And if so, then you basically create that branch, you advance the token, you add it, and then you go to the inline check. Now, this is something very important. So I'm going to go to Paint here. Whoops. Now, when we're processing our dot notation call expression, this is, you know what, I don't even need Paint, actually. I'm just going to show you guys on the back end. So now this is where it gets into like murky waters when it comes to figuring out how you should do certain things on your parser. The only reason it is in this formatting is because I've been building my programming language for so long and I know my language and I kind of already know what is the easiest way to process information. So when I was first writing my parser and I was allowing the user to have what's called an after expression. So you basically have your main expression and then you have your secondary expression, which complements the primary expression. So like if you have this function, whatever this function returns, this function must this after expression must complement that, right? So if you return like an object, you can't plus plus an object unless, of course, it has a operator overload. If it has an operator overload, then that's totally fine. But it's contextually based, so it requires whatever the primary expression was returned, and then you use the secondary to complement it. So if I go to compile here, I'm going to go to compile expression. And we can see here that, like, let's go to the example where we have the self or the function and then a plus plus. So if I go to my compiler, I'm going to go to primary expression, parse dot notation call expression. So we can see here we have our AST dot function E, and then we have this function called compile method utype. Now I'm not going to go into how this function works, but all you need to know is this just basically tries to figure out what are you trying to call, and it returns a method if it resolved the function properly. But what's important is down here, and this is called compile post AST expressions, or the after expression of whatever you are processing. So if we have the example where we have function plus plus, so we want to basically continuously tack on expressions to this branch here by simply just adding them as sub ASTs instead of like nesting them. So hopefully I'm making sense. I feel like I'm doing a pretty bad job at explaining it. So basically what I'm saying is when you're writing your compiler and your parser, you're going to have multiple iterations of how you're going to format how your AST is going to be generated on the parser side. So all I'm saying is just don't be surprised if you have some retarded formatting that when you start writing your parser for the first time and you get to finally the back end side of your compiler and you start looking at the format and it looks bad, just know that you're probably going to have multiple iterations of improving how it's formatted so that way you can process it a lot easier. So if we go back, we can start looking at left brace. So this is the case where you have a function, then some left brace here. So you're basically processing an array. So first you're going to want to create an array branch. So you're going to create a AST array expression. Advance, you want to add the token. You don't really need the token, but whatever. So I'm adding the token. Then you want to parse the expression. So what this is going to be is this is going to be what's called the index expression. So you parse the left brace, and then you want to parse the index expression that's going to go inside of it, and then you want to close it off by parsing the closing brace. So that's what that is. And as you can see here, you are processing the closing brace immediately after. Now, as a compiler developer, you have to think about every possible situation and whether or not it's ethical to do or it makes common sense to do. That's besides the point. You need to support everything. So what if you have a function dot some field, right? What if you call a function that then basically accesses an array index, and then you want to call some field or you want to access some field after you have processed this information? Well, this is where you get into some interesting situations when it comes to parsing your language. And this is why you have to be very meticulous and thinking about how you write your parser and making sure that everything is supposed to be connected. Nothing should be like put into a corner and it'll eventually hit a dead end. Because when I was writing my parser, one of the biggest mistakes that I've made is that I didn't allow for what I call complex expressions. So like you could even go even crazier. So you could say like some function, and then you could say at some other index. So let's say at 1, and then we can say plus plus, and then let's say that plus plus is an operator overload that's returned from this array expression, which represents some class or some shit, and then you want to, I don't know, then maybe access some field there. So, I mean, again, this is disgusting, but you want to be able to support situations like that because as a compiler developer, you have to be able to adapt to every single situation. So, and we'll see how on the back end I process that clusterfuck of expressions. So that's going to be pretty interesting. But with enough rambling, you can see here that immediately after that, I check to see if the next token is equal to a dot. And if it's equal to a dot, then I basically enter protected mode, grab the old token, parse a dot notation call expression, and that's going to recursively call back into here and have this crazy wacky formatting. And if that did not parse successfully, then of course, because there's no guarantee, then we want to reset the current token. Then we want to ignore the errors that were generated and free up the last sub that was created as a result of this function call. Otherwise, if it was in fact processed correctly, we want to print out any errors that may have happened in the process and go from there. Otherwise, let's say maybe you have something else after this. So like, let's say maybe you have like a left paren. Now, why would you need this? So here, I created a quick example for you guys. So let's say we have some function that basically returns a array of function pointers. Now, in this case, the function pointer has no parameters and it has no return type. Now, I just did that for simplicity's sake. But let's say we want to access the 0th index of that function pointer. Now we need to call the function pointer. Well, that's where this comes in handy, right? So now let's say we had, I don't know, let's say this function pointer took an int as a parameter, and we can say like 7, and we can call it using this formatting. So that's kind of why we need this left paren here to basically call another dot notation function expression. So what you want to do is you want to parse the expression list, and you want to encapsulate again this into a dot notation function expression. And if any of this makes sense to you guys, the reason why we want to continuously encapsulate this is because if you think about it on the compiler side, when we start generating our code, we want to start from a top-down perspective. So when we start compiling it, we're going to say, all right, well, we want to process or we want to call this function pointer here. Well, how do we call this function pointer? First, we need to get the index of the array that was returned from some function. Well, how do we get the index of the array returned from some function? Okay, well, we need to call some function. So it starts from the top down, but it starts generating code from the left to the right. So because everything is recursive, we again start from the top, but then we need to generate this code first, then this code, and then this code last. So that's how we end up having the effect of calling things or accessing our data from a left to right perspective. So that's kind of why I have encapsulation here, and this is also why I'm recursively calling into dot notation call expression, because it allows us to leverage recursion in an effort to generate our code appropriately and in the correct order. So after that, you want to go to increment check. So once we go back up to increment check, we finally have our last check here. So if it's none of this, if it's not increment, decrement, if it's not left brace, it must be this format here, where we have some function and then some field. So we enter protected mode, get the old token, recursively call back into this function, and this is basically the same code that was up here. So if it was successful, we complain about any errors. If it failed, we reset the old token, ignore the errors, and then free up the last sub that was created as a result. So that's pretty much it. That's how we parse a dot notation call expression. Now, let's look at the formatting for all of these various different situations. So here, what I'm going to do is go back here, delete the noise, and we can just, now since we're doing this on the parser level, we don't have any semantics running, so we don't have to worry about the fact that some function doesn't exist. We just want to look at how it's formatting. So let's just look at some function first. So we're here. Now let's kind of see how our self-expression is formatted. And then once we look at the format for self-expression, then we can jump into seeing all of the various formatting for dot notation call expression. So if we look here, we can see we have our self-expression. It's inside of our primary expression. And we have our, oops, let's pull this up. So we have our self and our pointer. Again, you don't need these characters. After that, we have our AST dot notation call expression, and this is the important stuff. So all we have at this point is just a U-type. So this is a naked U-type of some function. So we just have type identifier of a reference pointer of some function. So that's pretty easy. Not too difficult to understand, but now let's kind of see all of the other different formatting for parsing a dot notation call expression. So if I go back to primary expression here, and scroll down to dot notation call expression, let's look at the situation where we have some function and we just call the actual function directly with no parameters. So if we scroll back, if we go back, you can see here, so if we go down to dot notation call expression, we have our function expression here. We have two expressions. So we have our handy dandy U-type, which, as mentioned before, you parse this information first and then this information second. So the second one is going to be an expression list, and it's going to be null because we don't have anything in there. Now let's say we have 1, 2, 3. If we go back, we should have 3 expressions that were generated as a result of this, and they should all be of type expression literal. So if we go back to our function here, or our dot notation call expression, we have our AST here, and then we have our U-type. So we still have 2 expressions in our dot function expression AST. So you have this one and then this one. But then after looking at U-type, we can see down here we have 3 expressions, because in our expression list we have 1, 2, 3. So we have a expression of a literal of 1, expression of a literal of 2, expression of a literal of 3. Now let's start getting a little wacky and start looking at some other situations that we may have, like some function plus plus. Look here, we have some function plus plus, so we can see dot notation function E, our standard U type, and we can see we have our expression list, which is empty, but then we have post increment E. Now, under normal circumstances, this would have encapsulated this entire piece of code here, but we don't want to do that. What we want to do is we want to basically tack on a crap load of extra expressions that are going to be processed after the fact, and they're supposed to be processed in order. So like, let's say we have, our plus plus, and let's say dot some field, because maybe this plus plus is a function call that's an operator overload that resides in a class that was returned from some function. So if we go to some field and have this crazy syntax, you can see here we have our post increment E, so we have our increment expression, and then immediately after that we have another dot notation call expression, which is just simply some field. So we can just see here, it's just a U-type of some field. So now if we go back and look at some other formatting, we can see here, let's look at this case where we have like an array. So if we create an array here, let's see how this one looks. We have our dot notation call expression, we have our function expression, 2 expressions of one of type U-type, empty expression list because it has no parameters, and then we have an array expression with our 2 tokens here. And in that expression, it's just a primary expression of a literal 0. So there's that. And finally, let's create just a wacky expression. So I'm going to do some function at 0 dot some class dot some other function plus plus at 100 minus minus some field at 300. Okay, so this is kind of absurd, but our parser, like in the past, this would completely create a segmentation fault in my parser because I would basically hit a dead end. Like if my parser wasn't so recursive and it wasn't created in such a way where it was like basically a web or a giant circle where it just processes the same information over and over again, then I would not be able to do this. So let's see what's generated here. So if we scroll up to the top, we can see we have our dot notation call expression. We still have two expressions here. So we have this expression and then all of this crap. So we have our function expression of some function. We have an expression list because there's nothing in there, so we don't have any expressions to process. Then we have an array expression. So our array expression has a 0 in it as our array index expression. Then after that, we want to access some field. So this is yet another tacked on thing here. So we can see we have a dot notation function expression. Now here's the difference. Because everything is recursive, this is now segmented into a completely separate AST. You can see here, this doesn't just have one AST, it has 5. Because basically once we recursively call dot notation call expression again, it creates a bunch of ASTs for all of this garbage inside of this AST. So that's where the recursion comes in handy. So we can look here, we can see we have a dot notation or dot function call expression. So we have our utype of some class dot some other function. So we can see here some class dot some other function. No parameters. We have a plus plus or a increment expression added on to the end of this dot notation call expression. We have an array of 100, which is tacked on to the end of this. So we have our index expression of a literal of 100. And then we have our minus minus. So this one, all of these are, like I said, basically attached to this one inner dot notation call expression. So if we scroll back down, if we go back to our minus minus, so we have that. And then we have some field at index of 300. So we have another dot notation call expression of some field here. And I actually just found a bug. Okay, so I'm actually going to solve this live. So if we go back up to our parse dot notation call expression, I have a bug where at the top of my dot notation call expression, I'm not forcing the user to process a dot. So basically that allows the user to do stuff like this, where you have your minus minus and then some field. So if we go back here, we can fix this. I'm going to do it live by just basically doing this. So in this example, we have, our plus plus or minus minus, and as we're like going through this loop to see what we need to process, whenever we call parse dot notation call expression, it's optional to have a dot here. But we want to basically make sure that if the next token is in fact a dot, then we can call parse dot notation call expression. Otherwise, the user's most likely going to get a parser error. And as you can see here, I'm even doing it here. So for left brace, like if you parse, an array expression, I'm actually checking to see if the next token is equal to a dot. And if it is, then I parse a dot notation call expression. Otherwise, I just ignore it, right? Like, of course, I have the situation where if you have a left paren. But yeah, so let's go back to the actual code. So ignoring that, now you guys see the fix for basically forcing the user to basically put a dot there. Moving on, we can see here we have our dot notation call expression. So here I'm going to actually just rerun this so that way I can show that the bug is in fact fixed. So if we go back here to some field, we have post increment. Now we have our dot. If you guys remember, and you can rewind the video a few seconds ago, we didn't have a dot here, and if we remove it, we should get an error. I will test that shortly after. But you can see here we have our utype of some field, and then we have our array expression with a index of 300. So this is, like I said, this is a pretty wacky expression. But doing it in this way allows you to basically have a dynamic, endless amount of expressions where the user can just do whatever they want. You don't have to worry about creating all these weird functions and edge cases to process all this information. So you just want to make sure it's recursive. That way you can just do things very magically. So now I'm going to do a quick test here, and we can see in real time what's going to happen if we parse some field. So I'm just going to hit play. And you can see here, we get an error. If I scroll up to the top, so if I scroll down, we can see expected semicolon right here. So you can see right at some field, we expected a semicolon because the expression is expected to end, and this is a variable declaration. So that is good. And yeah, so that's going to be it for today, guys. Hopefully that wasn't too much information. As usual, if you guys have any questions, definitely put them in the comments section below. So as per usual, I'm going to go over to my GitHub repository. So if any of you guys would love to help support the channel, definitely head over to my GitHub repository at github.com/androdevcd/sharp. And when you do, definitely watch, star, and fork the repository. It's going to give the language a lot more visibility and let other developers know this language exists. Also, if you guys are curious about maybe things that are going on in the day-to-day with the language, kind of as I build it, I would recommend heading over to the remastered branch. Anything else other than master or remastered is completely stale, so just keep that in mind. And when you head over there, you can check out the commits. I put some pretty wordy commits on there. I've been pushing commits a lot less frequently, but they've been more massive commits. So I've just been committing less with more code versus committing a lot with less code. But nonetheless, you can check out my commits here and you can pretty much get a gist of what I've been doing with the language thus far as updates, so on and so forth. Also, if you're curious about maybe things that I'm looking to add to the language or maybe stuff that I've done in the past, you can definitely head over to the doc folder. And in there's two main files you can look for. So you can look at the change list file, which is basically going to be a list of all of the changes and updates that I've made to the language in the past. And you can head over to the roadmap file, which is going to pretty much be everything that I've done to the language thus far, including all of the features that I'm looking to add to the future. This file is a very interesting one, so I would highly recommend you guys check that out because I have some really cool stuff in there that I'm looking to add to the language. So that's going to be it for today, guys. Definitely like, comment, and subscribe if you guys like what you saw and you want to see more. Until next time, I'll see you guys later.